All right. Yeah. So like Sebastian said, I'm a PhD student at the University of Melbourne. I've been here for a year now, and thanks to Sebastian, I will be staying for a second year. So this is more an introductory presentation on the kind of stuff I'm looking at, the assumptions I'm taking, the definitions of the problems, and kind of where the meat of the problem I think is. Yeah. So just to start, just to acknowledge the right things to begin with. So my research is funded by the Australian government, the Australian Research Council. They have a research center called OPTIMA, which stands for the Optimization Technologies, Integrated Methodologies and Applications, which just opened a year ago. So it's just a big research center that combines a bunch of research interests and a bunch of universities. I'm from the University of Melbourne as well. And so I've been here for a year, thanks to Professor Andrea Lodi, which is with the chair, but now we'll be staying for a second year thanks to Sebastian and Gerard. So that's everyone. Yeah, so I've got a toy problem that I want to use to kind of illustrate the different subproblems I'm looking at. I'm going to give a proper formal definition of these. And then, like I said, I'm going to tell you about what I think the meat of the problem is, which is integrating the low fidelity data in bi-fidelity problems. So first of all, just to give you the definitions, again, I think a lot of you guys have very similar problems and ideas, but I want to make sure to be clear what I'm assuming in case there are some very slight differences. So when I say bi-fidelity expensive black box problems, there are three keywords. The first one is black box, which I think is the same for you guys. Essentially, we have a function for which we don't have an explicit formula, right? So the only way to extract information is to sample. So, you know, y equals x squared, not a black box. I know what it looks like. I know how to optimize it analytically. If I don't have that function, it's a black box. Expensive. So what this means is that sampling the function has a very high cost. That is either expensive or it's time or any other reason. So essentially, the kinds of techniques that you use in these types of problems are different because you assume you can do whatever you want aside from sampling the black box often, right? So normally what this means is that you can train very accurate models, which take a very long time to train, just because you don't care how long they take. They might take an hour or 2 hours to train, but then sampling the function might take you a day or a week, or it might take you $10,000, right? So anything that isn't sampling the function, you can do whatever you want, take as long as you want. And then when I say bi-fidelity, and I guess that's kind of specific to me, I have two sources of information, which I'm labeling FH and FL. The high fidelity describes limited correct information. So this is my expensive black box, it's the truth. And then the low fidelity describes a second source, which is cheaper. So I've got more information, but it's less reliable. And so the key question here is that, well, the key idea is that you assume the low fidelity source has some value to it. And so in the literature, what happens all the time is that people create techniques which integrate the two sources. And so this can arise from a variety of reasons, right? So just to name a few, you might have a model which is very complex to evaluate, and this is your expensive black box. You might simplify this. You might have a simpler physics model, which is a low fidelity black box. So it gives you less accurate information. It runs faster. You might also have a model which has a mesh grid that takes a long time to evaluate. If you make the mesh grid coarser, you get something that evaluates quicker, but it's not as accurate. And then in industry, an example is experimental versus simulation data. So gathering experimental data might be very expensive, and you might supplement that with a physics simulation engine, which runs very quickly, but it's not as accurate. So this is my toy problem, Australia. So the topology of Australia actually is quite surprisingly, it's a very nice black box to look at, just because it has very deep seas around Australia, but the land itself is very flat, and it has only a very few tall mountains in the country. So the squares, the blue squares are the cities, the capital cities of the states and territories of Australia, and the red triangles are the highest point of each of the states and territories. But most of them are very low, right? They're not very tall. The only real tall mountains in Australia are down here and down there, right? So anyway, this is a black box because at a latitude and longitude, which gives you a coordinate, a position, you have an elevation. Obviously, you don't have a rule for this elevation. It's expensive in this toy problem because to get the elevation at a particular point, you need to send in a team of engineers, which is very expensive. And you might have two possible aims. One is that the Australian government might have asked you to come up with an accurate map of Australia. but expensive to do so. How do you do it? And the second one is they might want to find the tallest point in Australia, right? So this is my toy problem. And then I've come up with two low fidelity functions to make this a Bi-Fidelity Expensive Black-Box toy problem. The first one, which is very common to see in the literature, is to just say, I've got existing records, but they are inaccurate, right? And so normally what people will do is they will have the truth, and they will add an error term to it, and they will say, this is my low fidelity source. So that's an example of this. I don't think this is very accurate in terms of reality, right? So I've come up with a second one where you say, the capital cities are very important and know their elevation exactly. And so I'm going to approximate the map of Australia by taking the average elevation of the two closest cities. And surprisingly, this is very accurate, kinda, because it actually gets you the land border of Australia almost exactly, right? The sea depths are horrible, and the elevation within Australia is also horrible, but you do get a rough outline of what Australia looks like. So anyway, these are two examples of what your low fidelity, what it could be like. So I believe there are three different sub-problems you can kind of define and try to focus on to get different insights on this field. The thing that is common to all of these is that I have two sources, like I said, my high fidelity and low fidelity sources. They are defined from some domain to the reals, right? They both have the same domain. And this is what I believe is slightly different from what you guys do here. So I'm assuming this domain is a hypercube. So for every dimension, I have a lower bound and an upper bound. There are no constraints, no hidden constraints, right? I kind of make my problem easier by assuming I just have very clear delimited bounds. I don't care about anything outside. I can access everything inside. And then a few other assumptions that might be different to what you guys work with. The first one is that the high fidelity source is the truth. The low fidelity source is cheaper, right? So I guess you could assume, you don't really need this assumption, but it's a bit weird to have something that is just an approximation, but it's also more expensive to evaluate. And this kind of distinguishes two different kinds of problems. I'm assuming both of my sources are deterministic, right? So essentially, once I sample once, I don't need to sample again. I have my information at the end. It's very acceptable to assume both of them are stochastic. And so the techniques here change a tiny bit because you might want to resample the same spot a few times just to understand what your error looks like. But I don't have that, right? So I'm just assuming once you've sampled once, you're good. So I've got three sub-problems. Each one becomes a bit harder. The first one is create a surrogate model with a fixed sample. What I'm doing here is I am given the two sources of information, and I'm also given some data sets. The first data set is my low fidelity sample. So I have a few locations which are a subset of the domain, and I've got the objective function at those locations. I have the same thing for my high fidelity function. So I've got a bunch of places where I know my objective function value. And normally what happens here is I assume that I've got more low fidelity samples than my high fidelity samples. The number of my high fidelity samples is relatively small. Again, for sampling, this is expensive, you assume. So normally you have less than 100 samples. And this is not necessary, but normally what you assume is that your high fidelity samples are a subset of your low fidelity samples. So normally why this happens is because you might gather a bunch of low fidelity information. And then once you have that, you might say, well, at these locations, I would like to supplement that with correct information. And then you want to integrate those two. So my aim here is to construct a surrogate model. And my way to assess the performance is to calculate the error between the truth and my model. This is a bit hand wavy here, and I will come back to this. The way to do this is to have a lot of high fidelity samples, like 10,000 or something, which obviously doesn't happen in practice because the high fidelity source is a black box. You can't have 10,000 samples. But when you're in a synthetic setting, which I will talk about more in a second, you have perfect information. You just assume you don't, right? So anyway, the way to assess performance is to calculate the error between what you've constructed and the truth. The second sub-problem is model creation, but with a sample budget. So instead of me giving you the samples and you don't get to touch the sources anymore, I am now giving you a budget and a cost ratio. So I'm telling you, you can sample the high fidelity source 50 times, and sampling the low fidelity source is 10 times cheaper than sampling the high fidelity source. So instead of sampling the high fidelity once, you could sample the low fidelity 10 times, right? So there's a trade-off there. where do you choose to gather your information from? And so the aim, again, is to construct a model. So you're doing this by gathering low fidelity and high fidelity data, and your constraint is that your budget cannot be exceeded. And so the way you calculate your budget is the number of high fidelity samples plus the cost ratio times the number of low fidelity samples. As an example, if your low fidelity source is 10 times cheaper and your total budget is 50, you could have 40 high fidelity samples and 100 low fidelity samples and combine them to create a model. The performance is the same as in the previous subproblem, just the error between the model you've constructed and the source of information. Now, this is the more traditional function optimization. Same deal, you have your sources of information, you have your sample budget, and you have a cost ratio, which tells you how much cheaper it is to sample the low fidelity source. You want to gather your information without exceeding the budget. And now all you care about is what is the best point you have found. And so this can be a minimization problem, find the deepest point in the seas of Australia, or a maximization problem. So you want to find the highest peak in Australia, right? And so again, this has always been my way of kind of defining the subproblems that I can focus in with my research, right? So I believe there are two types of analysis you can do here. So the first one is a synthetic setting. So always we're assuming that these two sources are expensive, but in a synthetic setting, they are not, right? So I maybe came up with some mathematical definitions, or I'm dealing with Australian elevation, where I can actually ask NASA to give me 20,000 elevation values in Australia, right? So I've got this perfect information, but when I conduct my model training and my optimization, I do this with a small sample, right? So I'm cheating a tiny bit because I'm using this very large sample to completely analyze the two sources, how they relate to each other, what they look like, but I'm not using this information when I run my algorithms. And so I believe this is extremely useful, not really what you see in the literature, because you actually get to develop guidelines for algorithmic usage. And I will come back to why this is important in a second. But essentially you say, if I had perfect information, what should I do? Which is a bit cheating, because if you had perfect information, you wouldn't be using these techniques. The second one is the more traditional applied setting, right? So you have limited information, you come up with an algorithm, you say, here's a new algorithm, here's how it works, and then you publish a paper, right? The key thing here is that normally when you do this, you apply existing guidelines, right? So you look at what people know of these problems, you use that to create a new algorithm, and then you submit that for publication. But if you don't have good understanding of the problem, this might not be a very good process. So anyway, these are the two types of setting. I'm more interested in the first one, which then leads to the second one. And so now I get to, like I said, the meat of the problem, which is how do you integrate low fidelity data into your model? So real quick, I want to bring up the model that I've been using in my research, which is kriging. So this is a pretty simple, not simple, but it's nothing new. This has been around for over 20 years. But essentially, it's a technique that's used quite often because it has a very nice, strong theoretical backing. So essentially, what kriging is a model. So if you're in D dimensions, you need to train 2D plus 2 hyperparameter values. So if you have 10 dimensions, this means 22 hyperparameters, which is a lot. When you're training these, you need to find matrix inversions, which the size of the matrices is dependent on the number of samples you have. So training this model can become something that takes quite a while, right? It's relevant to these problems though, because I don't care, right? So if I'm assuming that sampling once takes me a week or $10,000, I don't care if training a model takes 2 hours, right? It also has a very nice exploration method. So if your aim is to create an accurate model, kriging will tell you, based on the information I have, I want to sample, I'm uncertain of my model in this particular spot. So you can aim to create more accurate models by sampling where you have maximum uncertainty. So you ask the question to your model, where don't you know what's going on? It will tell you, you sample there. And then it has a very nice exploration versus exploitation combination. So when you're trying to optimize, you want to, one, learn more about your sample space. You want to find good areas. But 2, you want to exploit. So once you found good areas, you want to sample there some more. So kriging has a very nice method here, which is known as expected value of improvement, which essentially it says, I, in this particular position, expect to improve the best point by this much. And sometimes this leads to sampling in areas that it knows nothing about, because it's like, well, I'm feeling lucky, maybe this will be amazing. and sometimes in samples in areas that it knows it's good, right? So it might think, I don't think I'm going to get a lot of improvement here, but I'm sure I will get a nice amount of improvement. That's all I'll say about kriging. The second thing to say is that co-kriging is just an adaptation from single source to bi-fidelity problems. Essentially, what all that co-kriging does is combine two sources, and then it does the same for exploration and exploration versus exploitation, right? Again, none of these are very new things. They're just solid things. Now, to give an illustration of why I'm using this stuff, so this again is Australia. This is a kriging model with 100 samples, right? So it looks like a bit of a blob, but really it has found deep seas around Australia, more or less. It has the generic shape of Australia, more or less. It's found the tall regions, more or less, right? With only 100 points, which, I don't know how to convince you of this, but I am impressed by this, right? So if I were to use a lot of models with 100 samples, this would not look this good at all, right? The second thing to mention is the graph that everybody shows about when they talk about co-kriging. This is kind of like the proof that co-kriging is incredible, right? So let me just go through this image. The notation's a bit different. Ignore it for me. What I'm trying to model, right, is this thinner line behind the circles. The 4 circles are the 4 available samples of high fidelity data. So that's the truth that is available to me. And then this dashed line is the low fidelity data function, and the squares are the available low fidelity data. So essentially what this image is trying to convey is the fact that I've got one source, the truth. I've got a low fidelity source, which looks nothing like it. If I train a kriging model, so only using the high fidelity data, I end up with this dashed line, which looks nothing like the truth. But if I create a co-kriging model, I get this thick line, which actually is almost on top of what I'm trying to model, right? So people show this image to be like, co-kriging is incredible. I augmented with data that doesn't look very accurate, but I get a very accurate model, right? Anyway, this is more or less the state of the literature. Things are changing now, but people just essentially believe that because you have a low fidelity source, you should integrate that somehow. And this is a clear example of why. So kind of what started motivating all my research is this guy, Thio, which in 2015 essentially asked, should you always use co-kriging in a bi-fidelity problem? So you have 2 sources of information. Should you use a method that combines the 2? And perhaps unsurprisingly, but it was kind of new when we published this, the answer is no, right? So you have 2 sources of information. Sometimes using the low fidelity source is harmful. So you actually do not want to use it. It's going to give you a worse model. You should ignore it. Sometimes, like a lot of people believe, if you combine the 2, you get a better model. And so what he kind of landed on is the fact that the correlation between the high and low fidelity sources is very important. So if the low fidelity source in general behaves similarly to the high fidelity source, amazing, you should use it. But if not, you should ignore it because it's going to be harmful. Now, more generally, this opens a bunch of questions, right? So the first one is, well, he talked about correlation, but really how are you going to distinguish different kinds of problems, right? So what is it that in a particular instance means you should ignore the low fidelity source, and in other cases, you should actually use it? So what specifically leads to this behavior? And also, how can you use a low fidelity source locally? So this is a bit harder, right? Instead of choosing, do you use it, do you not use it? Is there situations where the low fidelity source is harmful overall, but if you were to use it selectively, it would be good, right? And these are kind of, believe it or not, kind of open questions with Bi-Fidelity Expensive Black-Box problem. So to illustrate my point, I'm going to show you 4 examples, but the setup is always the same. So initially, I put down 50 low fidelity samples. I choose a subset of 25 of those samples, and I get high fidelity samples. I give that to my model, and then I say, off you go, right? So if I train a co-kriging model, I give all of this information, and I say, your aim now is to create an accurate model. Every time you sample, it will gather a low fidelity and high fidelity sample. I do the exact same thing with the kriging model, with the same initial samples, but instead of giving it the low and high fidelity samples, I only give it high fidelity samples. So kriging ignores the low fidelity stuff, right? I do this 5 times, I take the average, and I check the results. And it turns out you're trying to minimize model error, that co-kriging is better than kriging, right? Standard literature stuff, right? Here's an example where this kind of looks like Australia, not really, right? But using this information is beneficial. I'm going to do the same thing with the same source, but now I'm trying to optimize, right? 50 points, 25, I run Kriging, I compare the results. Now I'm trying to maximize, I'm trying to find the highest point in Australia. So at the very end, Kriging kind of comes in for the win and is higher, right? But for most of the time, Kriging is clearly doing better. Not surprising, right? So when I'm trying to create an accurate model, I want to use this source. When I'm trying to optimize, I want to use this source, right? Fake conclusion, you should use the low fidelity source. If you come up with new models, you should use this. All right, let's move to this one. So maybe as a mini quiz, right? This kind of looks like Australian. Should I use this? Like if I run the exact same thing, is it going to be better to use this source? Or is it going to be harmful to use this source? It turns out it's harmful, right? So this kind of gives you a generic shape like Australia. It looks similar, but if I use this and I train a co-Kriging model, my performance is worse than if I train a Kriging model. And now perhaps the thing that I think is even more surprising is that if I now run the same thing, but I'm optimizing, using this source is actually good, right? So when I want to create an accurate model, bad, don't want to use it. But if I'm trying to optimize, good, I should use it, right? So what is it about this low fidelity source that actually is beneficial when I try to optimize? As I kind of answer, it turns out that because I'm taking the average of capital cities, and Australia has a lot of capital cities down here, which happens to be where the best point lies, even though it's pretty bad everywhere else, where it matters is really good, right? Which again, I thought when I was entering this field that this was kind of like, again, of course, right? But this is not really something that really people think about, right? So you need to ask yourself, intuitively it makes a lot of sense, but what is it that I should be measuring about this low fidelity source that tells me I should use it? And I shouldn't use it when I'm trying to create an accurate model. So I guess to kind of explain why I think all of this is beneficial, right? So in 2015, like I said, Thio presented a study in the synthetic setting. So he looked at on the perfect information. So if I know exactly what my high and low fidelity sources look like, when should I train a co-Kriging model? When should I train a Kriging model? And the answer is, well, unless the correlation is very high, you shouldn't use co-Kriging, you should use single source Kriging, right? Here's where you might say, well, this is cheating because they have perfect information. But this actually motivated two later studies, which are very nice, I think, in the applied setting. So in 2019, a very nice study from Muller presented a Bi-Fidelity function optimization algorithm, which doesn't assume you should always use the low fidelity source. So essentially what it does is it finds a place it wants to sample. It asks the question, does this look like a place where the low fidelity source is beneficial? If the answer is no, it ignores it. If the answer is yes, it uses it, right? The way it asks, is it beneficial, is by checking the correlation between the high and low fidelity sources. Something that was found by looking at the synthetic setting, right? So looking at the synthetic setting led to nice developments in the applied setting. 2021, something similar happened, but now with a model, when you're looking at creating an accurate model overall, so not in the field of optimization. So now is where I want to tell you just quickly the stuff I've done, just to situate myself. Just realizing that it's going to be a short talk, right? Perhaps it'll be nice. So we have published a paper called Bi-Fidelity Surrogate Modeling, showcasing the need for new test instances. And essentially, so first to tell you what we looked at. So again, in the synthetic setting, so I have perfect information of my instances. I looked at the simplest problem. So let's have a fixed low fidelity and high fidelity sample. Let's train a co-Kriging model or 20 co-Kriging models with different samples, 20 Kriging models with different samples, compare them, check which one's best. And so actually what we found, first of all, is that the instances that people tend to use in the literature are not very varied, right? So essentially what's happening is that people are coming up with the first low fidelity example I gave you, but they just kind of add an error or they modify the low fidelity source a tiny bit. And so when you do that, you always want to use the low fidelity source, or it's very clear when you have to use it. But if you look at instances that are more like the second low fidelity source, it becomes a bit more blurry. And so what we did was presented a new way to generate instances, which I'm not really going to go into. And also new features. So new things you might measure about these two sources to tell you which model you should use. And so essentially what we found, which kind of contradicted the work from Thio, is that you don't care so much about whether the low fidelity source is accurate there always or overall. What you actually care about is how often it is locally accurate. So in some regions it could be horrible, but then in many other regions it's great. That's great. That's awesome. You want that. Whereas it could also be that overall it's horrible, but then in select regions it's very accurate. So in optimization, that might be a good thing. But when you're trying to create an accurate model, that's not a good thing. So currently what I'm working on, right? So the previous paper essentially kind of had a quick look and presented a few features, and we found this concept that when a function is locally accurate, often that's a good thing. Now we're trying to look at more features, right? So we're looking at 200 features. So not only how the low fidelity and high fidelity sources relate to each other, but we're also using landscape analysis. So essentially, what does a high fidelity source look like? What does the low fidelity source look like? What does the difference between the two look like, right? So if the difference between the two is 0, for example, which doesn't happen, but if it were, then the low fidelity source is amazing, right? Because they're identical. It could be that sometimes it's 0 and sometimes it's very different, right? So what does that mean? We're also looking at a variety of samples from the low fidelity and high fidelity sources. So in the previous paper, we kind of stayed on problems, but now we want to say, well, if you have 5 high fidelity sources, what should you do? If we have 20, if we have 50, if we have 100, right? And then there's a special case that I'm kind of looking at now that's giving me a bit of a headache, but there is a special case where the low fidelity source has no cost, right? So this can happen. You, for example, in the second low fidelity source example I gave you, there's no real cost in taking the average between 2 cities, right? That's done instantaneously. So the high fidelity source is expensive. The low fidelity source is not expensive. What do you do? Turns out there's no real answer that I found. So kind of working on that. And then the idea is to do essentially another iteration of what has already happened, right? So Thio said high correlation is what matters. Other researchers implemented that. Now we've shown, well, actually something else matters a bit more. The next step is to integrate that into new techniques. And then potential future work, just some ideas that could lead to new things, is to expand this analysis to many other variants of this field, which there are plenty of, and the techniques could change quite a lot, specifically from a lot of what I've been hearing and learning from being here. The first one, which is an obvious question that people ask me a lot about, is stochastic black boxes. This is not easy to apply to just because the techniques change a lot. So like I mentioned, the very basic thing is that you might want to repeatedly sample the same place just because you're gathering information about the stochasticity of that black box. So techniques are quite different. The second one is black boxes with constraints that I know Sebastian is working on, and definitely a point of focus in Montreal. And also multiple low fidelity functions. So this also makes things quite tricky. So you could have fixed low fidelity functions. So you could have 3 different sources that you have access to, or you could have a source that has a parameter, right, which is continuous. So essentially you have an infinite amount of low fidelity sources. How do you integrate that into all of this? I have no idea, but it would be a very interesting question. And that's everything. So yeah, thank you. And if you have any questions in French as well, I'm happy to answer them.